Okay, we are really going to finish 2.2. We're just going to finish it now on the iPad. So we're going to try going back to that same slide that we were on with example 3, and we're on part C, which we called set C, and we called the last one set D. Okay, so on set C, our goal here is to find the number of items in these particular sets. So either that's a counting argument or that's looking at the numbers and deciding. So this set of numbers looks a lot like when we were doing sequences, right? I have a set that starts at 1 and ends in 99. Excuse me, and I know that this set notation says x squared such that x equals these items. So the actual set, if we were to want to write them down, would be to take each of these numbers 1 through 99 and find their square. That's what this actually says I'm going to do. So if I were to actually want to write this set down, this would be the numbers 1, 9, 25, 7 squared, which is 49. And we would go all the way up until we got to 99 squared. I mean, that's what this is describing. Does that make sense? But that's really not what we're asked to do in the problem. This problem actually asks us to find the number of items. So it's equivalent to asking us how many items did I square. That is, how many numbers 1 through 99 odd are there? And how many are there? Do you remember? How's it work?
Isn't this the same thing we did?
Mm-hmm. So how many? How many? 50. And why are there 50, Kinsey? Exactly. So if we were to go from 1 to 100, we'd have 100 numbers. But we don't have all of those numbers. Namely, we don't have the evens. We only have the odds. So half of them are odds. So there's 50 of those. Make sense? We're used to doing it with the evens. We haven't seen it with the odds quite as frequently. All right, the next set then is n of d, or is D, and we're going to look at the number of items in set D. So let's take a look and think about this one. This one says all x such that x equals x plus 1. So we want all numbers where the number equals the same value as that number plus 1. So for example, if you were to take a number, so give me any number you'd like. Just give me a number. 5, thank you, and we had it in unison even. So if we took the number 5, does 5 equal 5 plus 1? No, this doesn't work. So 5 is not an example that works here. So what numbers would work here? What number equals itself plus 1? Does 0? No, doesn't work. Does a negative number work? If we did negative 5, would negative 5 equal negative 5 plus 1? Nope. Yeah, there aren't any, right? This is no solution. This set right here is equivalent, we used this notation last time, to the empty set. There is no number that equals itself plus 1. So how many items are in this set? 0. There are no items in this particular set. Does that make sense? So you're going to have some where you're going to interpret this sort of set notation and take a look at that and counting. Okay, so let's move out of cardinality, and we're going to move into another topic in this section called Venn diagrams. You have seen Venn diagrams before if you've taken contemporary math. A Venn diagram is simply a diagram that used to illustrate an idea in logic. There's a universal set. That's the set that contains all the elements you're talking about. And then we have something called a complement of a set. So if we have a set F, then F has a complement. And the notation is a little different than in the contemporary math book. The notation looks like F with a bar on top. Okay? In contemporary math, that notation looked like a prime. They're interchangeable notation. There's actually a third notation, too, that would look like an F with a, sort of looks like an exponent of C for F complement. But your book is using this notation right here. And this is actually just defined to be all elements in the universal set that are not in F. So I'm going to draw a picture of what a Venn diagram looks like. And it looks like a rectangle with circle or circles inside. That's what a Venn diagram looks like. So let me change my size of my circle. I'm just going to draw a picture of what's going on in this particular description. The universal set U is the big rectangle. The sets that are inside of the universal set are represented as circles or circular shaped items. If you do an oval, that's fine. And so if this item inside of this circle is F, then F complement is considered to be everything in the outer part of the rectangle. So it's all of this. So that's what the Venn diagram sort of representation for that looks like. Let's talk about an actual concrete example of what this looks like when you find a complement. So if we have a set U, and U is the universal set, and it's describing all of the students at OBU. Okay, so my big rectangle is OBU students. Got an idea of what that means, right? So I'm not in that set, right? Because I'm not a student, I'm a faculty. Okay, but all of you are in that set. All of your roommates and your, friends and stuff that are here at OBU, they're in that set. A is the set of the graduating seniors. So what is a complement? So first of all, it's all OBU students who satisfy a condition, right? Because it still has to be inside the OBU rectangle. So this is all OBU students. And is there a way more concise to say freshmen, sophomore, juniors? Everyone not. It's not just seniors though. Yeah, it's everyone except the graduating seniors, right? So this is all OBU students who are not graduating seniors. And you're right, so this is going to include all our freshmen, sophomores, and juniors, and some of the current seniors as well, right? Those who simply aren't graduating yet. Does that make sense? So when we're talking about a complement, it's just the negation of what we were talking about to begin with. And that's what this is. We talked about the graduating seniors. These are not the graduating seniors, or the seniors who are not those who are not graduating seniors. Let me say it that way. All right. All right, so if we have a subset is simply a set inside of another set. So you have a set A and B is a subset of A. The way that is written is like this. And this B is a subset of A if every element in B is an element in A. Okay? So your family, your immediate family, is a subset of your extended family. Like when you talk about your family that gets together at Christmas and Thanksgiving, right? You're just a smaller group of people that are considered family, but when you say family, you may mean a broader sense of people as well. That's a subset. Okay? Those graduating seniors at OBU were a subset of all students at OBU. They would also be a subset of the seniors at OBU, wouldn't they? Yeah, because all of them are seniors and they're graduating, so it's a little bit more restrictive to be a subset. We also have something called a proper subset. So proper subset has the following feature. It's a subset, first of all. Okay? That's important. It is a subset. And the notation for it looks like this. Oops, I get the wrong one first. I did B. Let me put it over here. This is the notation for subset. B is a subset of A. If and only if B is a subset of A, and the other condition is that B is not equal to A.
Is that like a C?
It kind of looks like a C. It looks actually more like a sideways U when you see it written in your textbook. Yeah. So what this notation here means is that B is a subset of A and they're not the same. Because you see, technically, a subset, or a set is a subset of itself. Because all it takes to be a subset is every item in one set being contained in the other. So if my husband and I, we've talked about this example before about my family being a set. If I were to describe my family and my husband were to describe his family, immediate family, they'd actually be exactly the same. Okay? So we could talk about my family being a subset of Jeff's family. We could talk about Jeff's family being a subset of my family. Because technically all it takes to be a subset is that every item in my family, every person in my family, is in his family. And that's true. It sort of seems weird, right? It's kind of like, and you've seen this before, with inequalities. We can talk about 1 being less than or equal to 1, but it's weird to talk about it like that, right? I mean, they're equal. Why would we even want to say less than or equal? Okay. But it's true. It fits the description. It's what we mean by that symbol. Now, proper subset excludes that possibility. I cannot write 1 less than 1. That doesn't work, right? In the same way, I can't say that my family is a proper subset of my husband's family. It doesn't work like that because they're actually identically the same. However, we could talk about my immediate family being a proper subset of my extended family because there are people out here in my extended family that are not considered part of my immediate family, right? So you're thinking like grandparents and aunts and uncles and such like this, right? Extended family. There are people that are included that were not included in the inner circle of family members. All right, there is a way to determine how many subsets and proper subsets you have. So if you have a set that has n elements, okay, that's the number of items in the set, then there are 2 to the n subsets, and there are 1 less, 2 to the n minus 1. That minus 1 is occurring not in the exponent, but down here after you do the 2 to the n. 1 fewer proper subsets. Because basically you throw out the possibility of the equal set. Okay? So I want to show you that this formula makes sense with a really small case. We're going to do a set of 3 elements. So let's say we have the numbers 1, 2, and 3. And I'm going to write out all the subsets. So if this formula is correct, I should have 2 cubed, or 8 subsets, and 7 that are proper. Right? There's 3 items in the set, 2 cubed, and 2 cubed is 8. So let me show you that that actually works with this case because it's small enough to do it. I could have the subset of just the number 1, or just the number 2, or just the number 3. Those are subsets of the original set. Everything in them is in the original set. What else could I do? 1 and 2, or 1 and 3, or 2 and 3. So I could put 2 of them and pair them up. What else could I do? Because I seem to be missing a couple. I don't have 8 yet. I can do 1, 2, 3. That's the one that is not proper, right? But it is a subset because of the definition of subset. The way we define subset, everything in that 1, 2, 3 set was in the original 1, 2, 3 set. There's one missing. Do you know what it is? The empty set, yeah. Okay, so it sounds weird to say, but the empty set is a subset of the set 1, 2, 3. Because by default, everything empty in the empty set, of which there's nothing, right, is in the original set. It's sort of like the uninteresting case. But it is a possibility. And if you count them now, I have 8 sets, right? If I remove this set 1, 2, 3, because it's not a proper subset, I'd have 7. So there's 7 that are proper. So that's how the process works. You can imagine if you had 4 items that this would get very big very quickly, right? Guess what's 2 to the 4th? 16. Do you want to write down 16 subsets? Probably not. And if we had 6 items, 2 to the 6th, is 64. You don't want to write that down. Okay, so this actual formula is very, very handy to have so that we don't have to write them out to figure them out. All right, so we're going to consider the set of all math faculty at OBU. There are 4 of us, which is actually not true anymore. My goodness, that's what happens when you don't go back and proof your slides, because there are now 5 of us. Let's make it 5. There are 5 of us. We hired an additional faculty member last year. Did you know that? 5 math faculty. It's very exciting. I know you're not excited, but I was pretty excited about it. All right, so we have 5 math faculty. The first question says, how many different subsets are there of the math faculty? So how would I figure that out without writing all these guys down? 2 to the 5th. And what is 2 to the 5th? It is 32. Very good. So there are 32 subsets of math faculty. There are 32 different groupings that I could create. Some of them have having just one person in them or no one in them. But there are 32 different groupings that I could create. How many proper subsets are there? 31. So just one less, right? 31. Now, question number 6 actually asks the question the other way. It says, suppose you have a set and you know how many subsets there are now. You don't know how many items are in the set, but you know how many subsets there are. And we want to figure out how many elements are in that set. And what would we do? Okay, so can I set it up sort of in an equation way first, Nicole? What would it look like? What? Let me say it this way. Yeah, there you go. 2 to the n. Well, it'd be minus 1 first. Equals my 127th. This is the proper subset formula, right? So this is the reason Nicole wanted to add 1. Because if we add 1, in essence, I'm trying to solve for the 2 to the n. I want to find out what n is. What's 127 plus 1? 128. It's the easiest question somebody's going to ask you today, right? Yeah. All right, good news. And then I've got to actually think about how I would find what 128 is with powers of 2. And your calculator will do it for you, right? You can just put in different powers of 2 to figure that out. So you try 2 to the 5th. Well, that's not going to work because that's 32. I already did that problem above, right? So it's got to be bigger than 5. So what do you have to do? What do you have to put in here to equal 128 in your calculator? What does it take? 7th. It takes the number 7. So if you play with 2 raised to powers, the power that it will take is the number 7. If you're not sure how to do powers on your calculator, just flag me when we're doing group work and I'll show you. Okay? So this is actually 7. So if there are 7 elements in your set, you will have 128 subsets, and that makes 127 proper subsets. With that simple formula, it has exponents in it, but it's not too bad to use. Okay? Any questions on that one? All right, got a couple more left. All right, so actually, you asked me, Nicole, about that symbol. This is actually what it should look like. See how it looks more like a U shape just flipped on its side than really a C? All right, there are 4 symbols at the top up here, and I'm sort of running 2 problems together. So you're going to have some problems that are asked you to pick between one of these 2, and you're going to have some problems that are asked you to pick between one of these 2. I just put it all into one problem, okay? So what we're going to do is we're going to go through first, and we're going to deal with this particular one, and then we'll go through and we'll deal with the other one. We're going to treat it like I've got 2 problems. I'm just answering the question with the same sets and stuff all the way along, right? All right, let's look at those 2 symbols first. Do you remember what that symbol was? I mentioned it last time. Is an element of. It means that the item that we're talking about on the left-hand side is included in the description of the set on the right-hand side. That's what it means. Okay? So we're taking a look first, and on part A, we have the empty set on the left-hand side, and we have a set with the number 0 in it on the right-hand side. And the question is, should I put the element symbol or the element symbol with a slash in it, which what do you think that means? Is not an element of it, right? Which one should go in that blank? And this may be the trickiest one on here, because the one that should go in the blank is actually the element symbol with a slash through it. And the reason is because what is that thing on the left-hand side called? It's an empty set. That thing on the left-hand side is a set, isn't it? It's not an element. By definition, it's not an element, so it can't be an element of what comes next because it's not an element. Are you with me?
The empty set isn't an element?
It's not an element at all, it's a set. Oh. It would be like kind of like saying if you talked about, all of you in here are ladies, and you talked about the sons of your parents. Well, by default, you don't get to be counted because you're not a son, right? This is what's happening here too. The definition of what the thing is on the left-hand side is that it is a set. I know it's a set that doesn't have anything in it, but it's a set. A set isn't an element. It's a set. So it's not an element. So we put the element with a slash through it because it just isn't one. Are you with me? Okay. Now, the second one's a little bit easier in the sense that if you look at the 15, it's not a set. It's an element, right? It's just a number 15. Okay? And if you look at the thing on the right-hand side, that set notation, what is that set notation describing? Can you tell? What does it mean to talk about all x such that x is equal to 2n? Not times the number of elements, but times the numbers itself. Yeah. Oh, thank you. Okay. So, Kristen, you say it's supposed to be even numbers, right? Yeah, and it is. This right here tells you that if you take a number, okay, it has to satisfy this condition. That is, it has to be double another number. So, for instance, the number 6 works because the number 6 is 2 times 3. But the number 5 would not be included because the number 5 is not 2 times another whole number or natural number. Won't work. So this description 2n is a description. It's a way of describing even numbers. What do you think, and you'll see it in your homework, if you were to see 2n plus 1, what would that be describing? Somebody said it. It's odd numbers, right? Because if 2n is even numbers and you add 1 to an even number, what happens?
Why is 2n even numbers?
Because if I were to take a number and I want to know, is it in the set? The only way it's in the set is if it's twice as much as some other number. So 5 is not in that set because 5 would be twice as much as a number 2.5, but 2.5 is not a natural number. Right? So it's supposed to be natural numbers doubled. And if you double natural numbers, you get even numbers. This description takes even numbers and adds 1 to them. And so when you add 1 to an even number, it turns into a odd number. So this is actually a description for odd numbers. All right, so is 15 one of these numbers on the right-hand side? It's not. Why? Because it's odd. It's not even. So if the right-hand side is a way of describing even numbers, then 15 is not an even number, so 15 is not one of those items. So it's not an element of the description on the right. Number 4. Well, part C, I have a 4. Is the set on the left an element of the set on the right? Okay, the answer is no. Question to you then is why not? It's not a number itself. It's a set. The thing on the left-hand side is a set, just like the original empty set part in part A was a set. So the description, it's semantics, right? It's how we're defining things. The definition about elements have to do with this has to be an element to begin with, and it's not an element. It's a set. It is. We're going to get to subsets in a moment. We're not doing subsets right now. We're talking about elements only. So hold tight to that. We're getting there, Kinsey, I promise. Right now we're just talking about elements. So this is not an element, right? Okay, part D. I've got the number 16 on the left. I've got a listing method with the dot, dot, dot on the right. What do you think? Yay, we finally have one that worked. What's on the right is actually a way of describing part B, isn't it? It is. It's a way of describing what's in part B, but in a listing method instead of being that set notation method. And 16 works finally because I actually have an even number. Okay, so Kinsey, you're chomping at the bit to get to the other one. This one right here is the one we're going to do next. Yes. Oh, I wrote the wrong thing. I'm sorry. I was so excited because I kept putting those little hash marks on. All right. All right, so now we're going to get to this other one over here. So this notation over here means it's a subset or it's not a subset. So in order for it to be a subset, it has to first be a set. So a couple of these automatically have no way of working out. Which two cannot possibly work? B and D. Why not? Because they're not sets. You can't be a subset if you're not a set. Okay, it's inherent in the definition. You cannot, none of you ladies can be sons because you're not a boy. You just can't do it. It's not possible. Sorry. You can't be anything when you grow up. You can't be a boy. Do you know that? there are some restrictions on what you can be when you grow up. Yeah. All right, so these two right here, they don't work. Okay, again, you're not going to do both of these particular things on the same problem, but I want you to think about them and see them kind of pushed together a little bit. All right, the other two actually stand a chance, right? Because they're sets. Hey, they got a 1 up on the other two already because they're sets. Now we just have to decide, are they subsets? Okay, so what does it mean to be a subset? Can you say it in your words? How do I make the decision if something's a subset of something else?
Like if it can go into the set.
Not go into it, but maybe if it's part of it. That's a good way of saying it. Is a part of it. Is the thing on the left, in this case, a part of what's on the right? We already know it's a set. That's the first condition, and it is that for A and for part D. I'm sorry, A and part C. Question is it part of it? All right, how about part A? The empty set. Is the empty set a subset of the set with 0 in it? Yes, it is. It's a weird one, right? But actually, by default, the empty set is a subset of everything, right? The empty set is a subset of everything. It's not an element, but it's a subset of everything. How about part C? Part C says I've got the set with the number 4, and then I've got this set with the numbers 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5. I've got yeses and nos. Maybe it would help us to rewrite the right-hand set in a simpler way. Kind of like when we looked at part B and we said, okay, what is this really describing? What elements are in this set on the right-hand side? This set that we were given in part C is simply a funny way of writing the set 3, 4, 5, 6. Isn't it? Yeah, that's what it is. So is the set with the number 4 in it a subset of the set with the number 3, 4, 5, and 6? Yeah, it is.
So it doesn't have to be exactly what's written in there?
It has to be equivalent to it. So 4 is equivalent to the number 1 plus, to the value 1 plus 3. So yes, it works just fine. It's just a description. All right, I think we have a couple more. I mentioned this in passing last time. This is the fundamental counting principle, or sometimes you'll see it called the fundamental principle of counting. And it tells you how to figure out how many ways something can happen if it happens in stages. So if you have an event M and it can occur in little m numbers of ways, and we have an event N and it can occur in little n numbers of ways, and if we do these two events back to back, then you would multiply little m times little n to find the number of ways something can happen. And the easiest way to see it is with an example with numbers, so let's actually do one. We have a 4-digit phone number, okay? So think about like extensions on campus. Yeah, I know you guys don't have phones on campus because you have cell phones, but your faculty members have extensions on campus, as do all of the different offices. So we have a 4-digit phone number. How many different digits could I have as my first digit in the phone number? There's actually 10, because it could be a 0, right? Now, there may be restrictions from the telephone company, but we're not given anything here to say that we do. So we have 10 items here. How many different options would I have for the second number in my phone number? 10. How about the third number? 10. And the fourth number? 10. They're all 10s. And according to the fundamental principle of counting, if I simply multiply the 4 10s together, that will tell me the number of ways I can get that 4-digit phone number. So where does 10 come from? Why is it 10?
Because you can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
That's why. Yeah, you have the digits 0 through 9. Yeah, so we want to remember a 0 in there. So what is 10 times 10 times 10 times 10? It is 10,000. There you go. That's how many different offices we can have on campus, 10,000. Wow, that's a lot, isn't it? We're nowhere near that. Awesome, we can keep growing. All right, part B. What if no number can be repeated? So we still have 4 digits. And we still have 10 options in option number 1. But how many would we now have in number 2? 9. because we already used up one of them in option 1, right? And then we would have 8, and then we would have 7. So what happens if we multiply 10 times 9 times 8 times 7? Half as many. Isn't that crazy? Half as many, and all I did was eliminate the ability to repeat a number. Okay? All right, last slide. Same idea. We're going to go to the mall, though, and we're going to we have 5 favorite stores in the mall, but we only have time to go to 3 of them. All right? So we have 3 stores that we're going to go to. How many choices do I have for the first one? 5. How many choices do I have for my second one? Is it going to be 5 or is it going to be 4? Why is it 4? She already went to one of them, and we're assuming that we're not going back and forth to the same places in the mall. That would be silly, right? You go in and buy something, you come out and you go in and buy something else. That would be odd. Unusual, anyway. And then the last one would be 3. So what's 5 times 4 times 3? 60. So there's 60 ways that we could do this. What if we get to go to all 5? What do we do? Which ends up being how many? It's 120 ways. And you may notice that this actually has another notation. This would actually be the 5 factorial you may have seen before. If you haven't, don't worry. It's not going to come up in this particular lesson, but it'll come back up again in, I think, Math 2. Last example, example 9. I want you to do this before you leave. You have to write something down. I want you to create an example in your real life of a null set. A null set is what? A set with nothing in it. I gave you an example last week of a null set in my life. The teenagers that live in my house. Very temporarily, I get to say the teenagers that live in my house is a null set. So what is a null set in your life? I gave you a second one too. I talked about the hamsters, didn't I? The hamsters that live in my house, null set. What in your life is a null set? Somebody give me an example.
Can I say like the pets I have in my room?
Yeah, sure you can. So the set of all pets that Kinsey has in her room, that would work. I think you're not allowed to, right?
Yeah, fish.
Fish.
My
Okay.
friend has
A crab. All right, what else? The boyfriend in Kristen's life. Yes, that would be one. You could give an example like that. What else?
the number of A's I have right now.
Oh, that's a bummer. The number of A's I have right now. Let's do one more, and then you can go. You guys just want to hang out with me longer, don't you?
My days off from work this week.
The number of days off that Katrina has from work this week. Okay, so you have the idea of what this looks like, right? Awesome.